the Charlie clock. Here's my breadboard project. We can see it display the current time, and when the switch is high, the stopwatch feature cycles and can be paused through this button. When the switch is low, it goes back to displaying the current time, making up for the time it lost, and the current time can also be altered manually as seen here. Here's the final product, which has a timer feature incorporated where you set the timer and the code counts down. We can also switch it back to the regular clock mode if necessary. Okay, so now for the code. The pins on the Charlie clock are defined, the switch and button pins are, as well as the RTC library. So the I2C address for the DS1307 RTC, typically 0x68, is conveniently hard-coded in the RTC lib.h library. In the Charlieplex clock project, an I2C connection to the DS1307 is set up by creating an object of the RTC DS1307 class with the line RTC DS1307 RTC, ensuring accurate timekeeping with the RTC module. Using the default I2C pins A4 for SDA and A5 for SCL, the RTC is initialized in the setup function with RTC.begin to check for proper connectivity, and if it's not running, the current compilation time is set with RTC.adjust. The current time is retrieved with RTC.now, setting initial indices for seconds, minutes, and hours, which are used to control the LED pairs for the clock display. The LED pairs are stored in arrays, and static integer variables, second index, minute index, and hour index, keep track of the active LED. These indices are declared static to ensure their values persist across multiple function calls, allowing the code to continuously cycle through the appropriate LEDs without resetting each time. A struct is a composite data type that allows you to group together different data types under a single name. This is particularly useful when you want to represent a complex data entity with multiple attributes like LEDs, which contain a cathode and an anode. There's also an input pins variable for clarity and a reset timer function, which is used for the stopwatch feature. The handle current seconds, handle current minutes, and handle current hours functions manage which LED pairs are illuminated by setting the relevant pins to output, turning them high briefly, and then resetting them to input to prevent interference from other LEDs. This method prevents overlapping and ensures proper display of the LEDs. All of these functions are under one function called handle current time for clarity. The cycling functions, handle second cycling, handle minute cycling, handle hour cycling, use the current time, current milli, to increment the indices based on elapsed time, advancing through the array of LEDs to represent the passage of seconds, minutes, and hours. Pins D2, D9, and D10 can speed up the cycling of either minutes, seconds, or hours when held high, simulating fast-forward functionality by shortening the update intervals to 20 milliseconds for seconds and 100 milliseconds for minutes and hours. The handle timer second cycling, handle timer minute cycling, handle timer hours cycling functions, they all do the same as the other handle cycling functions, except they don't have buttons that dictate how fast they should switch between the arrays. In stopwatch mode, which is activated when the switch pin A6 is high, similar cycling functions are used, but without the button speedup feature. It also sets the indexes to 0, as it is now in stopwatch mode. So the loop function manages this mode, determining whether the clock should be in regular RTC mode or stopwatch mode based on the state of A6. When in stopwatch mode, it pauses or resumes cycling based on the state of the pause button, which is D10, and if the switch pin goes low, the clock reinitializes the time from the RTC and resumes normal timekeeping. This structure allows seamless switching between clock and stopwatch modes while ensuring accurate LED cycling and user interaction. Thanks for watching.